All right, this is how we're going to have an example of calculating for a calorimetry lab. Keep in mind that this number here is not the same as your dry lab data. So this is just purely an example. Your dry lab data will give you an unknown for your metal, unknown for your salt, and then it will have different sets of numbers here. But I'm going to walk you guys through how we can calculate using these numbers here as an example. So make sure you look for your dry lab data. It is in an Excel file under the student dry lab data folder. Okay. All right. So the first thing we want to do is this is the recorded data that will be provided for you. You have part A, and then we have part B, and then we have part C. So it's 3 different sets of calculations that we will have, pages after this that we have to fill up and calculate on our own. So make sure that you are showing work for every step here, making sure everything is shown, all the work calculations, it needs to be shown in your book, okay? So we'll go ahead and get started. Now, the first part is we have to get the mass of water. So mass of water is simply mass of the calorimetry and water minus the empty calorimeter, okay? So that would be, in this case here, I guess I can try to fit the work in here. So it would be 85.050 grams minus 30.000 grams. Now this is an example. It's not going to be the same number as what you guys have. And that's going to come up to 55.050 grams. Now remember, if you're subtracting a number, you keep the smallest number of decimal places. In this case, I keep 3 decimal places. Now, let's keep going to the next step. It says temperature change of the metal. Now let's take a look at the change of the metal. Well, temperature change would be the final temperature of the metal minus the initial temperature of the metal. And when we take a look here, final temperature of the metal is here. Water and metal at the final step, they have the same temperature. So this is my final for the metal, and 100 degrees is my initial for the metal. So final minus initial would be 29.0 Celsius, final minus initial of 100.0 Celsius. Again, I'm subtracting, so I have to keep the smallest number of decimal places, which is 1. So I'm going to get negative 71.0 Celsius. Okay, now let's take a look at the temperature change of the water. My final for the water is the same as 29 degrees Celsius. My initial for the water is 23. So final minus initial for this water would be 29.0 Celsius minus 23.0 Celsius, which would give me positive 6.0 Celsius. Okay, now how do we calculate heat absorbed by water? So Q of water's formula is Q equals to MCS delta T, which, so I'll go ahead and show the work over on the bottom here. So this is heat absorbed by water, part A. So I'll write the calculation down here, part A, heat of water. Okay, we will need mass of water times the CS of water. So specific heat capacity of water is given to us, and in the textbook you'll learn it's 4.18 joules per gram Celsius, okay? And then you'll have to do delta T of the water, which is the change in temperature of the water. We've already calculated that, right? We calculated that earlier and it was 6 degrees for the water. So why do we do the heat absorbed for the water first? We have to actually solve for the water because we have all the information for the water. We have the mass of water, which is 55.050 grams. CS of water is 4.18 and the delta T of water is 6 degrees, okay? So let me zoom out a little bit to help you guys. Just a little bit so we can see the whole page. There we go. Okay, so now I'm going to go ahead and fill this in here. So mass of water calculated is for my example, 55.050 grams times 4.18 joules per gram Celsius. And the temperature change is for water is 6 degrees Celsius. So I'm going to get a positive value here. So it's going to be pretty big, but I'm going to end up keeping just 2 sig figs here, right? So let's put it in the calculator and see what we get. So 55.050 times 4.18 times 6.0, I get 1380.654. So that's surely a lot of numbers. We don't need to keep all of that. We will only need 2 sig figs. Why? Because that guy has 2 sig figs, okay? So when we have this here, let's write it in scientific notation, 1.4 times 10 to the power 3 joules. Okay, so when we have this here, we have this value. So what we're gonna do is now, because water and metal are opposites in energy, basically the hot metal, when you put a piece of hot metal, you drop it into some cold water, the metal loses heat and it gives the heat to the water. So whatever the water's energy here, that it came from the metal, okay? So this water received 1.4 times 10 to the power 3 joules of energy, and this came because the metal released that same amount of energy. So essentially, Q of metal is the opposite of Q water, which means same number, opposite sign. So that means it is negative 1.4 times 10 to the power 3 joules. So whatever you end up calculating here for water, it will be the opposite sign for metal, okay? Because at the end here, when they reach the same temperature, when they both have 29 degrees Celsius, because final temperature for metal and water is 29 degrees, so they're at thermal equilibrium. All of the energy from the metal, all the heat from the metal has now transferred to the water, whatever heat they wanted to transfer, it's all done. And basically, metal lost 1.4 10 to the power 3 joules, water received 1.4 10 to the power 3 joules. Okay, now if I know this value for metal, I also know the formula for the heat of metal, which is going to be mass of metal times CS of metal. So the specific heat capacity, this is what we're looking for. That's the answer for the next step. And then we'll have the delta T of the metal, which we calculated. We said it was negative 71 degrees Celsius earlier, okay? So let's take a look up here again. So we had this negative 71 here. This is for the metal. And we also had the mass of metal from earlier, because when you weigh the metal out before you do the experiment, there's a mass of the metal over here. Okay, so that goes into my formula down here. The mass of metal, the 17 grams plus the delta T, which is negative 71 Celsius, is going to be a big negative because it's going to drop from a really, really hot temperature and it's going to go down to, in this case, 29 degrees Celsius. If I have this, this, and this, I can actually solve for the CS of metal, which then goes over here to find my answer. So meanwhile, while we're at it, I'm going to go ahead and fill this up what I just calculated. Heat absorbed by water is 1.4 times 10 to the power 3 joules. We just calculated that. Okay, so let's keep moving here. I'm going to go ahead and fill in these two values here. Negative 1.4 times 10 to the power 3 joules equals to 17.330 grams of metal. Now remember, this number here came from the previous page if you have your trial 1 under recorded data. Okay, this will be your dry lab data, but remember your numbers will be different. So I'm going to put that number right there. CS of metal is I'm trying to look for, so I'll leave that by itself, CS of metal. And then delta T of the metal is negative 71.0 Celsius. Okay. So let's go ahead and solve for this. So basically take 1.4, negative 1.4 10 to the power 3 divided by this value and divided by that value, you get CS of metal. CS of metal It's going to end up being a pretty small number, but it's going to be a positive value. In this case here, with 2 sig pigs, it ends up being 1.1 joules per gram Celsius. Okay, it should be a really small number and positive value. Hopefully you calculate something like that with your set of data. Remember, your answers will be very different. Okay, so I'm going to go ahead, once I get this, I'll put this up here. 1.1 joules per gram. Okay, since we're not doing trial 2, you'll really just have to do one trial, get this answer right here. You can leave the average alone since we don't actually have 2 trials. If they ask for the average during their online results, just say we only did 1 trial, so there's really no average. All right, let's take a look at part B. So part B here, the first thing they ask for is the mass of the water. So how do we get the mass of water? We have to take a look at part B's recorded data. So basically part B here, you're taking some solid here, and then you're going to dump it in water and see if the salt, when the salt dissolves in water, if it gets hotter or cooler. In this case, we're observing it get cooler, okay? So to get the mass of water, you take the calorimeter and water minus the empty calorimeter mass. So it'll be 84.255 minus 30.000, okay? So in this case here, it's 84.255 grams minus 30.000 grams. I'm going to keep this 3 decimal places, and my answer is going to be 54.255 grams. Okay, total mass of the solution, which is mass of the water plus the salt. In my case here, I put in 5 grams of salt. So unknown sample is the salt, okay? So 5 grams here, 5.00 grams plus the water would give me the total grams of the solution. So I can go ahead and write this down. This would be 54.255 grams of water plus 5.000 grams of my unknown salt, which would give me 59.255 grams of solution. Okay, now what is the temperature change of the solution? So let's take a look at the data again. When you take a look at the data, you see the final temperature is 15.0 Celsius. The initial temperature is 22.0 Celsius. So over here, I can actually say temperature change would be final, which is 15.0 Celsius minus initial, which is 22.0 Celsius. So I'm going to get a change of negative 7.0 Celsius here. Okay, so notice every time you add or subtract, you keep the smallest decimal places. So in this case, I'm keeping 1 decimal place. Now the next part here, they ask you to calculate what is the energy absorbed or released by the solution. So the reason why they say absorb or release, because we have 2 scenarios. In this case here, the solution is actually getting colder. Okay, so when something is getting colder, it's because your water or the liquid part is actually losing heat to supply the energy to give to the salt to dissolve itself. So the process of dissolution from the salt will be a positive number over here. Okay, but because the water, it is getting cooler, you will end up getting a value that's going to be negative here. So let's take a look at how we can calculate the energy for the solution, okay? So part B, I'm going to write it down over here. Probably use a different color pen this time. Let's see if I have a black color pen. Okay, let's take a look here. So for part B here, Q of solution. So Q of solution here is going to be mass of the solution. And then we have CS as the solution, which is given. So this is CS, and you assume this is 4.18 joules per gram Celsius. And then we have delta T, okay, of the solution. And the delta T is this value right here. So let's go ahead and put this in. The mass of the solution is 59.255 grams because we calculated it here. And then CS 4.18 joules per gram Celsius. And then my delta T is negative 7.0 Celsius. So this is why I say, you know, the value here for the solution will be negative. That means the number for the salt, the unknown itself, will be a positive value because, again, the solution and the salt are going to be opposite numbers. Same number, opposite sign. So let's take 59.255 times 4.18 times negative 7.0. And I'm going to get a negative number, negative 1733.8013. So again, it's a really long list of numbers. No need for that long list because all we're going to keep is, in this case here, just two sig figs. So it ends right here. So I get negative 1.7 times 10 to the power 3 joules right here. Okay, so once I get that Q solution, I will know that Q of the unknown is positive 1.7 times 10 to the power 3 joules. The way this works is these guys are going to be always the same number but opposite signs. Part A is the same way. If this one's positive, the other one's negative. So this one's negative, this one has to be positive. Okay, so once we get that, let's go ahead and fill this in. So obviously, if it's negative sign, it's going to be released. So it's 1.7 times 10 to the power 3 joules. And then this guy absorbed it. It's 1.7 positive 10 to the power 3 joules. Okay, now, so let's go ahead and get the enthalpy of the solution per gram. So enthalpy of the solution in this case here, all we do is we take by the value over here, the positive value, they really mean enthalpy of dissolution, the process of dissolving. So let me rewrite this. This is enthalpy of dissolution. Okay, the process of dissolving per gram of solute. So you take the Q of your unknown, so enthalpy of solution, is positive 1.7 times 10 to the power 3 joules divided by, it says per grams of solute. And how many grams of solute did we use? We actually used 5 grams. So 5.000 grams right here. So you remember your values will be different, but you just look for the same numbers, location of the numbers, okay? So take that 1.7 10 to the power 3 divided by 5. And we'll end up getting 340. So 3.4. Actually 3.5 because it's 4/6. So we'll round up 3.5 times 10 to the power 2 joules per grams. Okay, so that goes over here. So you just divide it by how many grams of the solute that you use. So that goes, this is positive 3.5 times 10 to the power 2 joules per grams. Okay? All right, so that's the end of part B. Let's take a look at part C. Part C here is going to be a little bit longer. So we gotta get the temperatures of all these solutions here. So let's take a look at our data here for the recorded data. So the volume is given. Now in my case, I have the same volume for both HCl and NaOH. I don't think your data does. Okay, so make sure you calculate accordingly. Now, temperature of HCl is given, temperature of NaOH is given. This is an initial temperature, and then the final temperature after mixing. So basically, if you add an acid and a base together, you undergo a neutralization reaction, and in this case, your neutralization reaction causes the temperature to go up. Okay, it gets hot when you do this kind of experiment. So let's go ahead and figure out what temperature we need to put in for the values here. temperature for the HCl is actually the same number. We had 23, so I'll show you where we got it from. Is 23 here, okay? So it's from your recorded data, whatever the number you get on your data. So 23.0 Celsius goes here, and then NaOH value goes here. And then they ask you to take the average of the two initials. Okay, so the average of the two initials, 23.0, 20 plus 23.1 divided by 2. And then with sig figs, you actually end up getting 23.1 degrees again, okay? So let me write it out. We end up getting 23.1. Okay? All right. So total mass of the solution, assuming the density of 1.02 grams per mil. Now, mass of solution, assuming you have density. So now the thing is you have to add up these two volumes here. So whatever the two volumes you have in your data, you add up. In my case, I have 50 mils, 50.0. Yours will not be exactly the same. So what you do is once you take the volume here, so basically 25.0 mils plus 25.0 mils for me, and you add that up, and then that's the volume, okay? And then you use the density of 1.02 grams in 1 mil, and then you can get the answer. So it's, my case, 50.0 times 1.02. Whatever the total of your volume times 1.02, okay? So I'll end up getting 51.0 grams here, 3 sig figs, okay? So whatever your mass is, you end up using there. You remember, have to use the density right here. Now the final temperature of the solution is right here. It's 35 degrees Celsius. That thing really got a lot hotter. That's really high, from 23 going all the way to 35. So basically, there is an increase in temperature of the solution. Great. So the solution part is going to be basically the water, and then we have HCl and NaOH inside the water. There's a reaction happening. So let's go ahead and calculate the heat of the solution first, which is the water component. So let's go ahead and calculate that. So for part C, heat of solution, so right, Q is heat of the solution equals to the mass of the solution, the liquid component. Your CS, they tell you to assume is 4.18 joules per gram Celsius again, and then we have to have the delta T of the solution, okay? Now, so delta T of the solution, we can calculate because we have the final and we have the initial. We have to take the average for the initial. So let me go ahead and put that in. So the mass of the solution we just calculated is 51.0 grams goes here. 4.18 joules per gram Celsius goes here. Delta T is going to be 35.0 Celsius, final minus initial of 23.1 Celsius. Okay, so this depends on whatever values you guys get here. Remember, your volumes will be different, so your mass will be different as well. But this is how you get your answer for Q of the solution. So obviously in this case, your Q solution is going to be a positive number. That means this reaction is going to be a negative number. So release is always going to be negative. Absorb is going to be positive. So let's go ahead and see what the number ends up being. So 35 minus 23.1, you end up getting, this number is going to be 11.9 right here, okay? So put a little bracket right there. So you take this times this times this, you get a big number here, you end up getting 2536.842. So again, really long list of numbers, but really we only need to keep 3 sig figs here, so it stops right there, okay? So, so that goes over here. So I'm going to go ahead and write down, I get 2.54 times 10 to the power 3 joules, okay? Now, again, because this is positive, the reaction is going to be negative by the same exact number. Okay, so Q of neutralization, which is the reaction, is negative 2.54 times 10 to the power 3 joules. Okay, now the next thing they want to tell you to do is to look for the moles of HCl and NaOH. The reason why is you need to find the limiting here. So how do you find moles? Well, the molarity of the solution is actually 2 moles per liter, 2 molarity per liter. So to get the molarity here, if you have to use the volume of the HCl and the volume of NaOH, okay? So 1 mole of HCl gives 1 mole of H, 1 mole NaOH gives 1 mole of OH. So you can literally just use the molarity of HCl and NaOH. So you would take 25.0 mils. In my case, I had 25. You take that and you work with the mole, turn it to liters. 1 liter has 1,000 mils. And then we also know that the molarity is 2.0 moles per 1 liter molarity of HCl, which is molarity of H plus here, okay? So you get a number of moles for H plus. In this case here, we're only going to keep 2 suffix, so 0.050 moles, okay? So I will do the same for a NaOH. In my case, I have the same volume, 25 mils again, so I'll repeat the same calculation. 25 mils, 1 liter, or 1,000 mils. Molarity of the NaOH solution is also 2.0 moles per liter, so that becomes the same value, 0.050 moles. Now in my case here, I have the same value, same number, so it's the limiting reagent or limiting moles is actually the same number because it's the same as the smallest. So all 0.050 moles have reacted. Now, if you have different numbers here, you would have to choose the smaller moles to be the limiting that goes down here, okay? So once you have the limiting moles, the smaller number of moles, all you do now, you can go to the next step. So enthalpy of neutralization, if you notice, this is Q in joules, but they want in joules per mole. So all you do is you take this joules and you divide it by that moles, okay? So enthalpy, so delta H of neutralization is negative 2.54 times 10 to the power 3 joules divided by 0.050 moles right here, okay? Because that is my limiting moles. So the limiting moles goes here, which is the smaller of these two. Now, put this number together here, we end up getting 5.07 times 10 to the power 4 joules per moles. Okay, so that goes over here, and it's a negative number. Don't forget the negative. So negative 5.07, sorry, times 10 to the power 4 joules per moles. Now, and then they tell you to convert to kilojoules per moles, which is then just divide by 1,000, because 1 kilojoules has 1,000 joules. So let me go ahead and write that down. Negative 5.07 times 10 to the power 4 joules per moles. We have this here, and you know that 1 kilojoule is 1,000 joules. So you get negative 50.7 kilojoules per moles. Okay, so that goes over here. Basically just divide by 1,000. And that is how you will do the calculation for part C. Hopefully this helps. Now remember, your data is in the dry lab data. Do not use these numbers that you see.